what I would do is a similar dynamic. It's kind of dynamic programming. I would say, I would ask the bird, how many quarters do I put in, right? And so this is me here. Isn't that a nice picture of me? We'll branch. Well, we could have 0 quarters, 1 quarter, 2 quarters, 3 quarters, right? And in this place we have 92 cents left, and we have 10 cents left, and we have 5 cents left. Oh, no, what am I talking about? We have 92 cents, and then, I mean, there's some amount here left, right? I'm not going to do the math here. I mean, in general, when dynamic programming is you try all the various things from the bird answers, and your friend normally gives you an optimal solution, right? But if the friend would give you the number of optimal solutions, and this friend gives you the number of optimal solutions, right? And you know that every solution down here is disjoint from every solution here, right? Why? Because this one has 0 quarters and this has 1 quarter, so we know they're disjoint. Then it's just a matter of adding these numbers to get the number of solutions here.
When, for example, the equation of 0, don't consider any more 25 cent point.
Yeah. Yeah. So, well, again, what are the, then we might ask, well, what are the sub-instances, right? Then it would be, how many, a prefix of the coins, plus the 92, right? So the table would be 92 wide and 4 high, right? Which this says how many of the coins I'm considering, and then I'm adding up to a certain amount, right?
Seems recursive.
Well, you certainly aren't, that's, well, not completely recursive, because it could be that some path down here and some path down here at the same level has the same set of coins that you have available to you and has the same sum available to you, right? So for example, this path takes 2 quarters, which adds up to 50 cents, and then this one takes 0 dimes, and this one takes 0 quarters and takes 5 dimes. And now you have the same sub-instance, which is I have these coins available to me. How do I make up 92 minus 50 cents? Right? So you can have some dynamic programming collapsing. But we still might ask, now what's the running time of this algorithm? Is this a reasonable algorithm or is this an ugly algorithm? How many people feel this is a polytime algorithm in the size of the input? How many people feel it's an exponential size algorithm? Right? Yeah, because 92 is exponential in the number of bits to write down to 92. Right? And this problem actually happens to be NP complete, so it's not too unreasonable. They call it, when you're actually counting the number of solutions, it becomes sharp P, and that's even worse than NP. So when you have to count. I'm not sure that helped anybody, but...
When you're doing that, though, when you say go down the path for 0 quarters, and you're saying how many optimal solutions are there, does that mean now you have to make like another branch where you'd say consider 0 dimes, 1 dime?
Yeah.
And so you have to build all those branches and say now how many optimal solutions are there with 0 quarters and 1 dime, and you have to keep going.
Yeah. So if we were doing a recursive backtracking problem, I would try 0 quarters, 1 quarter, 2 quarter, 3 quarters, and then for each of these they would try a certain number of dimes, and for each of them they would try a certain number of nickels. And then you just add up, you can see you add up the solutions and you get the answer, right? And now what he was saying is, well, what we're doing here sounds recursive, and the dynamic programming savings is that some of these do collapse.
How many great answers would there be now? Because every level answer is different amount of good chances.
Yeah, I mean it would be, yeah, sometimes it's variable, and you'd have to sort of, I mean that comes up sometimes. Sometimes, like with graph search, the number of bird answers depends on the degree of the node.
And you won't get this, right? Because 3 years ago it was something like that.
For me?
You will get this?
I would say it's not a completely unreasonable question had we talked at some point about counting the number of solutions, right? But we haven't talked about counting the number of solutions, so. We have now, though. He pointed out that we have now. So now it could be on the exam. Yeah, I certainly have in the past spent times on counting the number of solutions, and I can't remember where, whether it was in where you have it, but certainly in the book. But no, we won't count solutions. Should we do another dynamic programming question?
Yeah.
Oh, that's what I was just thinking. Yeah. Yeah, in fact, I was just thinking that. We just have to threaten our computer again. I don't have any slides for it, except for things cut out of the book. But here's a picture out of the book. All right, so suppose that you want to do shortest path, just like Dijkstra's works great, except what happens when you have negative weights on the edges, right? So Dijkstra's doesn't work. So, for example, here, what's the shortest path? Well, anybody know the length of the shortest path from here to here? Well, you could go 1, 4 certainly is an option, right? What happens if you go around, right? Then what do these add up? This gives you a -1, right? So going around once gives you 3, right? But if you could go around twice, then it could give you less and less. If you go around an infinite number of times, you get negative infinity. So you have to be careful what your question is even, right? If you want to say, do I allow really long paths or not? Now, actually, if you allow, if you ask the question, what's the length of the shortest simple path where it doesn't use the same edge twice, turns out to be NP complete. So, so we're not going to do that. Right? But if you allow here for this answer to be negative infinity, then we can do it dynamic programming. All right? And this is a pretty, I'm not sure actually running through this example is going to help much with your ability to do dynamic programming because it's a bit of a complicated one.
If you allow it to be negative infinity, isn't it almost trivial? Because as soon as you find something where you're reducing your values, you just get it forever.
Yeah, so if you ever have a negative cycle and you can get to it and leave to it from S to T, then the answer is negative infinity. Right? So, but still, you could have the example where there are negative cycles but you can't get to them, and it could be the case where there are cycles with negative edges but none of them are negative cycles. Right? Anyway, one way of thinking about dynamic programming is the bird-friend algorithm, but we could also sort of jump in and say, what are the sub-instances we want? And so sub-instances might be you define some prefix of the, you sort the nodes in some order, and say we're only considering the first so many nodes, right? And then for every node I and j, you want to know what's the shortest path from I to j that can start at I, and then it goes through as many nodes in this range as you want, and then it has to end at j. Right? So that's everybody understand what the subproblem is? Yeah? No? Yes? No. All right. So we're going to have we're going to have a big three-dimensional table. Right? Here's our table. Right? For every I, j, and m, we're going to have a subproblem. And the problem is the shortest path from I to j with nodes in 1 through n minus 1. The internal nodes. Right, so what do I mean by here? We have a path, it starts at I and it ends at j. Why? Because that's where we're going. Right? And all the nodes in between have to be in this range. Right? So that's a problem that we might want to solve. And how do you solve it? Well, we solve it with dynamic programming. If I want to know the shortest path from I to j, that all internal nodes go through things from 1 to m, then I can ask the little bird, how many times do I visit m? Right? And what are the answers? Well, it's possible I never visit m. Right? In which case, we just delete m and then we use the answer that we had from the table. Right? Right? If we say the path from right, we're trying to solve this instance I, j, m, right? And if the bird says you never go to m, if m's not in there at all, then we ask the friend about this instance. Right? Does that make sense? Yeah, maybe. You lost? What? Yeah, if she says when you're going from I to j via everything between 1 to n, you never go to m, then you just say, hey, I never go to n. So the answer has got to be the shortest path from I to j, where in between I use nodes from 1 to n minus 1. Right? Another option is she says you go to m once, in which case you look for the shortest path from I to m, where you only go through nodes between 1 and n minus 1, right? So, so my problem is I, j, m. And I ask how many times do I go, the number of times to m. And if she says 0, then the answer is I, j, n minus 1. Right? And if she says 1, then the answer is I, j, I, m, n minus 1, and then m, j, n minus 1. Right? I go from I to m with these nodes, and then I go from m to j with these nodes, and that gets me from I to j with 1 through m. All right, people follow those two ones? And what's another answer she might give? Right? Would she ever say 2? No, she won't say 2, because if you go there twice, why did you go there twice? It was because it was useful, right? So you might as well go an infinite number of times, right? And in this case, it's the same as this, right? This and this are the same. but you also go from m to m with m minus 1. Right? This is where you're looking for a cycle from m to m that has negative weights. And so if you're doing dynamic programming and you've already solved these problems, then you can solve this one. I think you guys are not being helped by this. Did anybody understand that at all? If what 0? If you go through.
If I go straight to J, like because
Why is M minus 1?
The number of paths, right?
Hmm?
The bird tells you the number of paths.
No, the bird tells you the number of times you visit M.
Oh.
Right? So here's the option. I want to know how do I get from I to J where I can visit these nodes in between? And the various possibilities are I could go from I to J visiting M 0 times, or I could go to I to J visiting M once.
But I mean, if you send an empty to where you want, wouldn't it just be 0 again?
Well, this problem says I want to go from I to M, and in between I can visit the nodes 1 through M minus 1.
Yeah. I mean for the 0 case.
The 0 case?
Wouldn't it always return 0 for all your friends too?
Well, this friend is now going to ask, how many times does M minus 1 get visited?
And it won't be 0?
Not if M minus 1 is sitting down here and is in there.
Oh.
Right? Question back there? Oh, I think this would be a brilliant thing to put on the test. Similar. Well, I mean, here's another classic one, which isn't too hard, and you should be able to do this on a test. Suppose I have matrices, n matrices of different sizes. This is in the book too, you don't have to write it down. Right? And you want to multiply them. Right? You want to multiply them all out. And one thing that's true about matrices, if you have matrix A and B, is that equal to B times A?
No.
No. But what happens if I have A times B times C? Is that equal to A times B times C?
Yes.
Yes, this is called transitivity as opposed to commutativity. Or maybe this is associativity. Associativity? What is this?
I don't know.
Don't know. Anyway, so you have these things and you can put brackets in lots of different ways. Right? And one way of thinking about it is it's a tree, binary tree, where the leaves are your matrices, M1, M2, M3, M4, so forth, right? And you want to know which binary tree gives you, for which this is the fastest. Right? And we don't want to get into too much of the math of it. Just believe me that if you do it one way and do it the other way, it's going to be different. Right? And so we're given the sizes of these matrices, and we want to know which binary tree is going to minimize the number of the amount of work we have to do. Right? Everybody understand what the problem is? So, what question should we ask the bird?
Should we multiply these two together? Then you get M1 and M2.
You're kind of asking about these leaves, right? What do you do here first, down here at the leaves? Is that what you're asking? Yeah. You want to try a different question?
What's the final answer?
So, remember we talked about various bird answers, and we said, you know, if the output's a tree, right? In this case, the output's a tree. What thing should you ask the bird?
The root, right? The root.
The root. The root. We ask the root. And what information does the root give? It's kind of a cut. It tells you what do you multiply last, right? It says first multiply these somehow, and then multiply these somehow, and then multiply the results together, right? And so we ask the bird for where to cut. And how many different bird answers can there be? N, right? It's a number of different places to cut. Everybody got that? And then what do we ask our friend? We've cut this.
So you asked how to
Left.
Yeah, we have one friend which tells us how to multiply the left, and another friend tells us how to multiply the right. And we put the two together to figure out how much this whole thing costs. Right? Does that make sense? All right, so if we were doing this on an exam, and you know, the dynamic programming parts of this are well within the expectations of an exam, right? The math, well, how many operations does it take? You know, what does this actually cost? You know, that's kind of fiddly, and I wouldn't want to have to do it on an exam. But we're not even going to talk about that part now, right? The parts we're going to talk about is first you have to say, well, what's the input? The input's the sizes of the matrix, right? What's the solution? The solution is a tree telling you how to multiply them, right? And then you say, given an input, and I pretend that the bird has one of these solution trees, what do I ask the bird? I ask the bird, what's the root, right? And the root tells me the split of the last things that got multiplied, right? So then, now we have a bird and friend algorithm. Everybody get what the bird and friend algorithm is? Anybody in doubt what it is? The algorithm is, I try all splits. For each split, I ask the friend, what's the best way to multiply these? I ask another friend recursively, what's the best way to solve these? I then take the cost of this, plus the cost of this, plus the cost of this last multiplication, right? And that gives me the cost of the best way to multiply my matrices together, subject to the bird was right. Right? Everybody following that? And then we try all bird answers, and we take the best of the best. Right? So that's a recursive backtracking algorithm. What's the next step? Somebody tell me how to do the next step in converting this into a dynamic programming algorithm. What do we have to do? What?
The sub-instances.
Yes, the set of sub-instances. We want to start with our instance, right? Our instance is a bunch of matrices, and we want to figure out what the set of sub-instances are, right? Ours are starting from 1 to n. Well, anybody want to guess what the sub-instances are? Are we going to get 1, 2, 3? Well, that will rise. Everybody who says 1, 2, 3 will be in there somewhere. Right? Why? Because the bird splits here, and you're giving it to a friend. It's a sub-instance. Right? 1, 2, 3 is definitely in there. How about 2, 7, 16? Is that in there?
No.
No. Why not? It's going to be. What about 7, 7, 6? Is that going to be in there? No. Right? We can take, this is a sub-instance, and then this is a sub-instance. What's true about all the sub-instances? They're contiguous, right? So a sub-instance is going to be mi plus 1, mi plus 2, to mij, right? This is a sub-instance that would arise. Everybody kind of buy that? All right, so this morning, I woke up far earlier than I would have liked to, and I thought about our discussion about indexing, how to build a table. And so I went downstairs and I spent a few hours making more slides. When in doubt, make slides. All right, what would the slides say? The slides in this case would say, we have our subinstances, and from those we want a mapping to the indexes. And from the indexes, we build the table. But you have to spell table right. All right? So what are our subinstances here? Are these guys. Right? So what are those indexed by? I and J. Right? But if you tell me I and you tell me J, then I know what the subinstance is. Right? And here we have I less than or equal to J less than or equal to N. Right? We have a range in there. So well, what does our table look like? It's a square. Right? And if this is I and this is J, and J has to be bigger than I, so that means this down here we ignore. Right? Does that make sense? Assuming that I gets bigger this way and this way.
Why are we able to do
What?
why?
Well, because I has to be less than or equal to J. Right? And so, what we need to do is every square of our, what do we need here is we need a table we need some data structure which is going to store the answer for every subinstance when it arises. Right? So we say, what are all the subinstances that are going to arise? Well, they're mi plus 1 up to mj. Right? These are the subinstances that are going to arise. We need a data structure which is going to store the answers for all of these. Right? So what's that data structure? Well, it's going to be some weird table. That table has to be indexed by something. So we want to index our subinstances by something. Right? What's this subinstance obviously indexed by? Well, it's I and J specifies it, because we know what all the matrices are. Right? The matrices are fixed. Right? They're fixed as part of the input. Right? Everybody know? Right? So this guy here, IJ, what's that square indexed by? It's indexed by IJ, but it's indexed by the subinstance. Given our matrices are mi through mj, what's the best way to multiply them? Right? And what do we write in this square? Do we write the tree, the solution? No, what do we write? We write the cost of the optimal solution for multiplying these matrices together. Right? And what else do we write? The bird answer. And what's the bird answer? Is where to split. Right? And then, when we're trying to fill in this thing, I have to think about it, but my bet is my friends are kind of here and here. Right? And you probably do something like this. Right? If she says split here, you do this. If she says split here, you do here. You split these various places. Right? This is my left friend, my right friend, my left friend, my right friend, and for the different splits. Right? Does that kind of make sense? Right? Because you're splitting at some k in between. So you're going from I to k and then from k to j. Right? So what order do we want to fill this table in? Can we fill it in this way? We got here? No, because we haven't done these yet. Right? So what order do we fill it in? We fill it in this way. Right? Which kind of makes sense, because we look at first, for every single matrix, how do we do it? Well, there's nothing to do it. That's the base case. Then we look at for every pair matrix, every two matrices, how do we multiply them? Then every three matrices, how do we multiply them? Every four matrices, how do we multiply them?
What do you put in if you can't multiply through the matrices?
Because the sizes are wrong, then the whole question is dumb. Everybody gonna get that? So now what's the running time of this algorithm? You should know this too. It's the number of bird answers times the number of sub-instances. And how many bird answers did we have? We had n. How many sub-matrices? N squared. What's the running time in cubed? Right, everybody got that? How many people feel you could write the code for this? You couldn't write the code? How many people feel they couldn't write the code? Could not write the code. Okay, good. Let's write the code then.
Before we write the code,
Uh-huh.
can you just go over
All right. All right, let's go through it one step at a time and really answer honestly because nobody's paying attention. All we're doing is counting, all right? How many people know what the instances is of this problem? So let's list the matrices. All right, let's not ask how many people know, how many people don't know. How many people don't understand what a solution is? All right, good, good. All right, the solution is so the people who are going to take my course from me next year will see how badly I work on the board. Step one is what's the instances, right? And it's a bunch of matrices, right? And it's their sizes, right? We don't actually care about the numbers. We just care about, and of course this size has to, so you're doing like this. This size has to equal this size to make him happy. Right? Everybody got that? Then what's a solution? A solution is a tree where you put M1 here and M2 here and M3 here and M4 here, so forth. So that's how you're going to multiply it. Right? You're going to first multiply these together, and then you're going to take the answer to that and multiply it with this.
How did you know that the solution is true?
What?
How did you know this is true? What is it because of
You know, I think, how do I know it was a tree? Well, I know that you take some things, right? If these are your matrices, I know I take some and I put brackets around them, which means that I multiply those together, right? And then maybe I take these two and I multiply them together, which puts this. Right? And then maybe there's a matrix here and I multiply this with this, and then I multiply this by this. It just feels like a tree to me. Now, would I make you think of that on your own? No, that would have been spelled out as carefully as I could in a big long explanation of the problem, and you guys would all say I didn't understand the problem. Right? But I would definitely, yeah, a diagram would be good. Anybody not understand the problem now? Right? And so given a tree, then I guess we want to know what's the cost of a solution, right? Given an instance, there are lots of solutions, lots of trees. Given a solution, we should know the cost of the solution. Well, let's not worry about how we would compute it, but given a matrix of this size and a matrix of this size, you could count what it costs to multiply. Right? It's going to be, in fact, this length equals this length, and the multiplying is this length times this length times this length. Right? And you add that up for all of these things. Everybody understand the cost? Anybody not? All right, so then we need a bird question, which is where to split. But split. There. See how good I am at this? Yeah, I mean, I just went to visit my my father for the first time in 13 years because he's mean. And he said, you know, oh, those crazy therapists who told me I was mean, you know, they also said that you were bad at English. I said, but I am bad at English. So anyway, that was kind of irrelevant, but I'm still bad at English. You know, I was in special needs classes all through elementary school, and I still can't spell split. But luckily, they gave me a job. All right, so we asked the bird, which is the last two things we multiply, right? And we're asking about the leaf, right? About leaf of the solution. No, you're right. Good thing. Good thing. About the root. I was just testing. Right? People get what the question is? And then we ask the friend, right? About, right? If this is our, you know, this is our split, we ask about the left and about the right. Alright? Anybody not understand this part?
Sorry, we asked the grade way to split, right? So if it says split index k.
Yes.
So
between k and k plus 1. Yeah.
K, okay. Alright, so then we take that matrices as a root and we divide.
Yeah.
So if there's like 5 matrices, then there's a split at between 4 and 5. Okay. So you take the middle one and then you send it to the rest. Well, the one that's
so we're going from mi past mk plus 1, mj. If this was our instance, then the bird says answers k, right? This is what the bird says. And this is our left friend, and this is our right friend. What?
The root would be the product of these two.
And then, so then what will our answer be? Is take whatever answer our left friend gives us, and take whatever our right friend gives us, and we join them. Right? So our cost is equals left cost plus right cost plus our root cost. Right? Whatever the cost of the root is. And what will that be? That would be, it's going to be this length times this mutual length times this length will be what our root cost will be. I don't know if you, I mean that really matters, but you know the matrix is going to have this size by this size by this size, and this one's going to have this size by this size. 4 minutes left. All right, boy. Everybody good with what the sort of the bird friend algorithm, right? And then we say, you know, then we try, you know, the set of sub-instances. So it's going to be mi to mj for every I and j. Everybody see how we kind of came up with that? Anybody not understand that part? All right, so now we need code. All right, so here is dynamic programming. The input is are, it's sort of M1 through Mn. Actually, it's their sizes is the input, right? We set up a table. We have one table index from 0, 1 to n by 1 to n, and it's cost and bird. Right? Everybody we got a table here? And then we got the base cases. What are our base cases of our matrix going to be? It could be the diagonal. Right? So loop I equals 1 to n, cost I equals what? You have just the matrix. How much does it cost to multiply all the matrices together? 0, right? And let's not even bother with the bird thing, right? Because say the bird could be whatever. And then we say loop over, there I have a sort of comment, loop over sub instances. Right? That's the next thing we always do. So here we're going to loop I equals 1 to, actually let's loop L equals 1 to n, loop I equals 1 to n minus L. We let I equal, we let J equal I plus L. So what's happening here is I want to loop this way, right? So we first loop over how many matrices we're considering, right? Actually, we should go up to 2 because we already did one matrix, right? And then there's probably a -1 here. I plus L minus 1 or something. Right? You have to, I won't take off marks for plus or minus 1 anyway. Right? But people can kind of see how we're looping through the thing here. Right? Because J is how far, L is how far up we are, and we try the various I's and various J's. All right, so now we want to say goal is to solve problem IJ, problem M1, MI up to NJ, and store answer in cost IJ. Everybody, what we're doing here? Our goal now is we have a particular square in mind, and my goal is now is to solve this problem, Mi to Mj. Does anybody not understand the code up to here? Anybody at all? Right? You know, we set up the table, we solve the base cases, we looped over the sub-instances.
Yeah, keep up.
You got that? Now we have a particular sub-instance we're trying to solve.
Can you explain that?
This bit here? Right, it doesn't really, we want to do them in this order so that nobody waits. Right? And how do you do it in this order? Well, you have this distance be J, or be L, you know, the distance up we are. And then you have this one, then I's runs from 1 to, well, you can't go too far, right? You can only go up to here. And then J is I plus L. I mean, just put...
What's the cutoff? Why did you slice it like 3/4 of the way down? Why did you say you can't go? Yeah.
Well, because This is the line. Here we have a particular value of I and the value of j that we're going for, right? And this distance is L, right? And I can only go up to here because else we're going off the end of the matrix. Those details don't matter to me. All right? You have to see, in English, and I would rather have a picture which says you fill them in this way, and you kind of guess how to do that. And if your picture is good, then unless this is really stupid, I'm going to ignore it. Right? If you did here, and if it was really stupid, I might take off 1 mark. But that's not what I care about. All right, everybody know what we're here? We're trying to solve this one instance. So what do we do next in the code? Everybody should know. I try to solve this. How do I solve an instance? I have an instance. What do I do? I ask the bird, right? But we don't have a bird. So we loop over bird answers. And so we loop k equals, what can k be? Well, I'm starting at I, right? So let's write I to j minus 1 or something, right? And then here we're saying bird says split mi to mk, mk plus 1 to mj, right? So now, everybody got that? The bird told us where to split. Now what do? We ask our friend, right? Who's our left friend? I to k, right? In fact, what we want to do is compute R cost. R cost sub k. What does this mean, R cost sub k? It's the cost of solving our problem, assuming the bird that's consistent with the bird answer. Right? So what's our cost? Well, the cost of, where do we get this cost? The cost of our left friend. It's cost I, k, right? What's the cost of our right friend? Cost k plus 1 to j, right? Everybody follow that? Now we need to, so our solution is to multiply these together, and then do the top. Now I'm going to have to guess here. I think it's the height of mi times the width of m k times the width of mj. But you would never need to figure that out. All right, everybody kind of buy something like that, right? You know it depends on I, it depends on j, and it depends on k, which is kind of reasonable, right? All right, now what do? Are we done with this bird answer?
No. The bird is otherwise.
Oh, but what's the bird advice here? Which is k.
Yeah.
So we loop over all bird answers. Right? Are we done with this one? All right, so we're done with that. Now we've tried all bird answers. Right? And now we take best of best. How do we do that? We let k equal kind of the minimum k, I don't know how you write that, argument of min of cost k, right? This means give me the k that minimizes this cost k. And if you want this code, it's in the book. It's in my book. I happen to know because I put it there. Everybody got this? And now, what do? we're ending these loops, right? We're now, oh, it's not quite. Right, now we want to store our answer. Right, where do we store our answer? Cost ij equals what? Equal cost k min. Let's call this k min so we know it's a, you know, which it is. Right, and bird ij equals what? K min. Right? I did all that work to figure out what is the best, my best cost. Right? Does that make sense? And then that I am now done. So I leave it up to other friends. Right? So we end loop. And we end loop. Right? And that fills in, you know, that fills in the entire table. Right? So now what do we have? Now we have this table filled in. Right? Does that make sense? Now we want to go back to the big problem. Our problem is to get from a multiply m1 through mn together. What's the answer? 1n. Was that remember, one requirement of your set of subinstances is that it includes the original problem. Right? Where is that stored in the matrix? 1n. That's 1n. That's sitting right there. Right? Funny, it's the last one we did. Why do I always find things in the last place I look? Right? Everybody get that? And but what's stored there is the cost, right? And the bird's advice. And so what do we do now? We do the recursive backtracking algorithm, but you have bird's advice. So you just follow the bird's advice. And it's easy peasy. And I don't ask you to write the code. Here you can just say, somehow I called it again, and you know, I don't require the code for that. Everybody kind of get that? How many people didn't follow something there? Anybody didn't follow something? You are going to have to do something this hard. Twice in the next couple of weeks. Right? It's just the truth. And so, I think we're out of time, but what you want to think about over Thursday is really look in your heart and ask yourself whether you could do what we just did here. Right? And if you have any doubts about any of the steps, then let's talk again on Friday. All right? And you might as well be doing this, doing the same thing about all the other topics. Greedy algorithms. Do you really in your heart not only understand the steps, but get why it's a proof? Because, if I could think of a question which tested you, do you understand why it's a proof? I would certainly ask that question. All right? I'm not sure how to ask it, but I will do my damnedest to ask it. All right? Have a good Wednesday.